This video is the second in a series of videos prepared to help you learn how to choose a probability distribution for your risk assessment work. In the first video, we handled the topics that are crossed out on the left of this slide. Following that system would enable you to go from a vast range of potential probability distributions to a relatively well-defined subset of distributions. In this video, we'll learn how to apply those techniques that you find on the right. Among the course resources you'll find for this module is an Excel database with eruption interval data for Old Faithful Geyser in Yellowstone National Park in the United States. If you grab this Excel database, calculated the mean and standard deviation, and assumed that the distribution of eruption intervals is normally distributed, you would run into a lot of trouble because the Old Faithful eruption data looks just like that figure on the slide in front of you. There are actually two distributions, one that roughly centers over hourly intervals and another that centers over hour-and-a-half intervals. So the point I would like you to take from this is a very simple one. Always plot your data. Always take a look at your data. Those bars that you see there, the vertical blue bars, are called bins. And if you have too few bins, it can distort the way your data look. If you have too many bins, it can distort the way your data look. So while you are learning how to examine data, I suggest that when you plot your data, vary the number of bins. Just about every software program will calculate a default number, and that's a good place to begin. But then try again with more bins and with fewer bins. I'll show you examples of that later using the at-risk software. But for now, beware that danger lurks if you do not look at your data. Data that would seem to be normal often are not. So have a look at your data. Once you plot your data, examine the plot. Here are a few of the distributions that come from the at-risk palette that we've seen before. And what you want to do when you look at your data is look for distinctive shapes of some specific distributions. For example, do your data have a single peak or is it a double peak like we just saw with the Old Faithful data? Are your data symmetrically distributed around that single peak? Or might they have a positive skew? A positive skew is when the tail of the distribution stretches out to the right. A negative skew is when the tail of the distribution stretches out more to the left than it does to the right. Does your data have negative values? So if you examine your plot, what you're looking for is to find out if your data look like any of the distributions here in this palette. Keep in mind that there are some distributions, we have not spoken of these, the gamma, the Weibull, and other flexible form distributions that are shape shifters. They have the flexibility to take on many different shapes. They are not bound, for example, as the normal distribution is, to always look like a Bell distribution. If you have succeeded in developing a small subset of distributions by learning about your data, and you get to this point of plotting your data, take a look at the shape, because the shape of your data may help you to narrow that subset even further. Those distributions within your subset that have a shape roughly similar to what your data look like would be good candidates for your final choice. Once you've gotten this far along in your probability distribution choice, then I would say theory is the strongest basis for making a choice. And that is a matter of opinion. That is not a matter of established fact. So you are certainly free to disagree. but in my opinion, this is the most compelling reason for the distribution that you choose. So let me talk about this idea of theory. Sometimes we have a very formal theory. Someone has posed a theory, someone has derived a proof for it, and we can rely on it with a great deal of confidence. For example, the central limit theorem tells us that if we have a sample statistic derived from a large sample, the sampling distribution of that statistic will have a normal distribution. So I would have a very compelling reason for using a normal distribution to represent the uncertainty about a sample mean, for example. But we don't have a great many examples of formal theory like that. So I would say, when I speak about theory, I would step down from formal theory and say the next level of theory is theoretical knowledge of the variable. You all are subject matter experts, and you know how these variables behave. If you are a financial expert, you know how stock dividends will behave. If you are a microbiologist, you will know how a bacteria will behave. And so this behavior itself gives us theory at times. That we could have a theory about the number of Vibrio that can exist in a gram of oyster flesh. You know, at some point the number of Vibrio gets too big and the flesh will not support that number. So this would be what I would call a theoretical knowledge of the variable that enables us to develop a theory about an upper bound on the number of Vibrio in the oysters. Sometimes there may be mathematical theories. There may be a mathematical reason why you choose a certain range. For example, probabilities are going to be frequent variables in risk assessments, and a probability is a number that is defined to exist between 0 and 1. So we have some pretty good mathematical reasons for why we would confine a probability to that range. So you've got formal theories, you've got theoretical knowledge that comes from your subject matter expertise. If you're an engineer, you might develop a theory about how an engineering system is going to behave and so on. Then if we step down one more time, I would say there's something that I'm calling informal theory. Informal theory is kind of grabbing insights wherever you can. For example, if we have a variable x that is the sum of several other variables, then it doesn't matter what those other variable distributions look like. The sum of those variables will tend to be normal. Products, if we have a variable x that is the product of several factors, it doesn't matter what the distribution of those factors are. The product of them will tend to look log normal. And so this would be an informal theory, so that when I start thinking about, let's say, houses, house prices, the construction cost of houses, I might begin to say, you know, that's kind of a summative variable, that the price of a house depends on the cost of excavating the basement, plus the cost of pouring concrete, plus the cost of this, plus the cost of that. And so I might develop an informal theory that housing costs are normally distributed. There can be study-specific informal theories. Suppose we were trying to estimate the amount of caffeine that a person would consume in a day, a random individual. I might develop a very informal theory that says, I think if a person drinks caffeine, they're more inclined to drink multiple caffeine drinks than just one. And my reason for that might be that a lot of people in my family, a lot of people among my circle of friends need that caffeine rush, and they need some caffeine injection early in the morning, and they need to renew it several times throughout the day. So informal theory is basically your best documented thoughts on a subject. So when you hear me speak of theory-based choices, it's wonderful if we have formal theories, but it's sometimes functional to develop an informal theory, as I've just described. When you do, be sure that you document it. These theories, formal or informal, can be used to further narrow down the subset of distributions that would meet your purposes for risk assessment. In my own search for guidance on how to choose a probability distribution, I very much wanted to hear some magical formula that says, calculate this number, and if it equals a certain value, use this distribution. Well, I can assure you that no such guidance exists. But summary statistics might provide you some clues sometimes. For example, if you calculate the mean and the median for your data, and they are approximately equal, and if you have plotted your data and they are single peaked and roughly symmetrical, then an equal mean and a median are a good indication of a normal distribution. Similarly, a low coefficient of variation would indicate a good chance that your data are normal. The coefficient of variation is the standard deviation divided by the mean. In some definitions, that number is multiplied by 100, so you would have to check a reference to find out what would be an acceptable value. However, low coefficients of variation are associated with normal distributions. High coefficients of variation are not. The exponential distribution has a positive skew, so if you're looking at data and its tail is skewed to the right, and you calculate the mean and the standard deviation and they are approximately equal, then there's a good chance that you're dealing with an exponential distribution. Sometimes you can consider outliers to help you figure out what distributions may or may not be useful, because some have tails that capture your outliers while others may not. Let's say a little more about statistical outliers. They're defined differently in different contexts, but usually a value that lies more than 3 standard deviations from its mean is a candidate for identification as an outlier. And the point for us is that extreme observations can drastically influence a probability model. If you are trying to put emphasis on all the data, those extreme values can sometimes pull you toward a distribution that might not best represent the population. Unfortunately, this is also a matter of art rather than science. There is no prescriptive method for addressing outliers. But what you do want to do is take a look at that data point. If it's an error, if it has been entered in error, then remove it from your database. If it's not an error, there's a temptation at times to ignore outliers because they make the work much more difficult, much messier. So this is when you have to ask what this data point is trying to tell you. What is it about your worldview that makes it inconsistent with this result? Maybe we need to amend our worldview. There are times when maybe we need to reconsider our perspective. If we were trying to put a minimum bound on the weight of an adult human being, or the average, or excuse me, a maximum bound on the weight of an adult human being, and we have a data point that is beyond that limit, the answer may not be to ignore it. The answer might be we really vastly underestimated the size and weight of adult humans. So think about the explanations that you have not yet considered that might help you better appreciate what the outlier is trying to tell you. When considering these outliers and what they're trying to tell you, keep in mind that the explanation that you come up with has to be correct. It's not enough for it to be a plausible explanation. That we've got a theory here that explains this data point. If our theory is correct, consensus is a poor measure of the truth. You really want to dig and delve for a correct explanation. If you have to keep the outlier and you can't explain it, then you can use conventional practices. That's largely what we're describing in these videos. and just live with skewed consequences. Or there are some distributions that are not as sensitive to these extreme observations. I mentioned earlier the Gumbel and the Weibel are two examples of distributions that can handle these outliers a little more comfortably than other distributions can. And they have that feature that they are shapeshifters, so you can often still get the basic shape and other qualities of a distribution that you want by using one of them. So imagine with me, if you will, that we have some data, but not enough to just use our data in an empirical distribution, and we've been going systematically through the steps that we've been describing. We've dealt with outliers, we've calculated some statistics, and maybe that's not helping us to zero in on the distribution. So previous experience is something to consider, and this is the point at which I would consider it. Have you dealt with this issue successfully before? Perhaps you have done a risk assessment and you have worked with water temperature data and you know what works because you've done it before. Or perhaps others have done this. Others have gone through a rigorous process and have found a particular distribution that's especially helpful. So always consider what other analysts did. Consider what other risk assessments used. Check the literature to see what the professional literature in your field might reveal about the choice of a distribution. And don't neglect your own experience. The more risk assessment you do, the more experience you'll acquire and the more confidence you'll build in your choice of these distributions. Goodness of fit tests are a nice piece of information to bring into the process at about this time. I'm going to provide you with another video that shows you how to use the goodness of fit software, so we won't go into the details now. But a goodness of fit test provides statistical evidence to test a hypothesis that your data could have come from a specific distribution. So you might develop a null hypothesis that your data come from a normal distribution. These water temperature data come from a normal distribution might be your default belief. You do a traditional goodness of fit test, a small test statistic, and a large p-value mean that you would fail to reject the null hypothesis. Or for shorthand, as I say here, you would accept the null hypothesis. So I believe my data are from a normal distribution. I collect some evidence. I test my belief. My belief fails to reject that. The evidence fails to reject my belief. So I'm going to go on believing that my data come from a normal distribution. It's another piece of evidence. It's not a determining factor. So if you or anyone you know is inclined to grab the data that you have, to move directly to a goodness of fit test, to run a goodness of fit test and see what distribution comes up first, let me say unequivocally, that is the very worst way to choose a probability distribution. So do not use goodness of fit tests to select your distribution. Once you've gone through all the steps I've described here, the goodness of fit test provides a nice piece of evidence to help you decide whether or not you have a distribution of a specific kind. Here's a sample illustration of one of the more commonly known goodness of fit tests, the Kolmogorov-Smirnov Statistic, or the KS statistic. Looking at the graph here, the blue line represents your actual data, and the red line represents a hypothetical distribution that has the same parameter values as your data. You can see that the red and blue lines do not match. So what you want to do in this statistic is find the biggest horizontal difference between the red and the blue line. And then basically you test that distance, the difference between the actual and the hypothetical value, to see if that is consistent with your assumptions about the distribution from which your data came. If the difference is too big, the test statistic basically says, no, your data did not come from this distribution. And if the distribution distance is less than that, then you would come back with a failure to reject the null hypothesis. We'll have more to say about goodness of fit in another video. The next step would be to ask an expert. I'm presenting it here as if you have been going through all these steps, including the goodness of fit, and you still don't know which distribution would be best to choose. But there could be many other reasons for asking an expert long before you get to this step. For example, you might be dealing with a situation where data were never collected. You don't have any information, or the data are too expensive, or it's impossible to get. There are many situations in which past data may be irrelevant. Sometimes you will have gaps in your database, perhaps because of the experiments that have been performed to date didn't cover the range of doses, for example, that you're interested in. And you might need to get expert opinion to fill those holes in some sparse data. In other instances, you could be looking at a new area of inquiry or a unique situation that never existed. In the past, I worked on the Houston Ship Channel project. This was a proposal to make a ship channel much wider than it is now. And with the greater width, there is a reasonable assumption that there will be fewer marine casualties in the channel. Vessels are less likely to run aground or to run into each other. And so if we estimate the probability of various numbers of marine casualties in a channel that has not yet been built, this would be a good example of an area of new inquiry or a unique situation that never existed. So this is when we would ask an expert to help us to identify the distribution. Who are these experts? Where do they come from? That could take us a week to discuss itself. But an expert could be somebody in your organization who's not working on your project with you, somebody across the hall who happens to know more about this topic than anybody else on the planet. So look inside your organization for experts. You may be surprised how often you can find them there. Other times the experts are recognized authorities. You can do a literature search and find out who is published in the field. You could ask experts in the field. Who are the experts? There are a number of ways to try to identify experts, including a call for experts, where we let people self-identify themselves as experts. Whatever way you do this, generally speaking, what you're doing is trying to fill data gaps with the person's experience. Sometimes those experts are people with reputation, and to be honest, sometimes people go out and will hire a well-known expert in hopes that this might intimidate anyone who would challenge their beliefs. That's not an especially pure motive, but it is a real one. What do these experts do? Sometimes we ask them to tell us what the distribution is. Is this normal? Is this log normal? What is it? They may be making judgments about the distribution of this value in a population. Other times they might be estimating parameters of a distribution. We may know we have a normal distribution, but we don't know what the mean and the standard deviation is. Other times we're having them estimate quantiles in the distribution. We're going to devote some time, some concentrated time, to consideration of expert elicitation. And so I'm going to leave this topic now just with the thought that hiring an expert, contacting an expert, finding an expert is a good next step in choosing your distribution. If nothing else, they can look over your shoulder and review your judgments to date. This concludes our conceptual discussion of how to choose a probability distribution. There will be a couple of videos that are illustrating these concepts, but let's consider a couple of takeaway points right now. Choosing the best probability distribution to represent variability or knowledge uncertainty is where many to most new risk assessors feel the least comfortable in their work. And the choice of a distribution does matter. Distributions generally come from some mix of data and expert opinion. The more data we have, the less expert opinion we need, and vice versa. And remember, distribution fitting using goodness of fit tests should never be the basis for your choice of a distribution.